Hello, friends. Welcome to my second video on applied deep learning course. As I told you before, these slides are for Professor Ali Barihi at Department of Electrical and Computer Engineering at University of Toronto. Okay, I hope you enjoyed the previous session on chapter 1, and we are going to have our course on chapter 2, feed-forward neural networks. I think this chapter has 4 sections. Let's go with it. Okay, we have various architectures for neural networks. We then call it NN for abbreviation because we will use it a lot. And yes, and we call feed-forward neural networks as FNNs, and sometimes some people call them FFN2, feed-forward neural networks, FFN or FNN. Yes, I confused it on myself, and yes, okay. And also some people call them MLPs or multi-layer perceptrons. But as you know, perceptrons are we cannot say perceptrons are exactly the same as neural networks, but it's not that much important. We can skip it now. Okay, we would call convolutional neural networks as CNNs and recurrent neural networks as RNNs. Okay. Yes, as you can see, here we have a neural network. We do not have any feedback. Why we are saying this? Because we will say some architectures that have feedback. Okay, the first type that we are going to talk about is fully connected feed-forward neural networks. It means fully connected FNNs. It means that each layer, for example, this input layer is completely connected to the first hidden layer. The first hidden layer is completely connected to the hidden layer. It means all of the possible A's are drawn. Okay. Okay, we know that we have L hidden layers and the depth is L plus 1, and if L is more than 1, we would call it deep neural network, and if otherwise we would call it shallow neural network. Okay, you would define the width of a layer. The number of neurons in that layer is easy. I think we can pass here. And but the important thing that it's not that much popular, but some people call the largest width the width of the network. Honestly, I have not that much seen that people want to call the largest width of a network, or for example, someone asks what is the width of this network. Honestly, I haven't seen that much, but yes, if you want to calculate it, you can write it as W, which is the width of the network, equals to max of all of the WLs. That L is from 1 to L plus 1, which are the hidden layers and output layer. Okay. So okay. As you may remember, we have some hyperparameters which are not learnable, and we have some other parameters which are learnable. Okay, and if we want to calculate this total number of parameters, learnable parameters that we have in a model, please note that I'm talking about a fully connected model. In this model, for we have WL plus 1 neurons in the layer L, so we can write this summation as you can see here. So we can write this summation from layer 1 to layer L plus 1, and for the first layer we can also write this. It is the input layer that we have this. You may remember from the previous. Yes, for example, you can see here WL plus 1. Oh, let me see. Oh, here it is from WL. Oh, yes, as you have seen here, it was my mistake, sorry. You see, from this layer, from layer 2 to layer L plus 1, we can have this formula, but note that for this layer we have n inputs. So here we have n inputs, it means we have n weights, and also we have also one bias. So the weight, this layer would have W1 times n plus 1 parameters, and also layer L plus 1 has number of for the number of width of the previous layer, ace, and one bias here. Okay, so it would be the total model parameters. Okay, now we want to talk about the forward path. Okay, when we have some data points, they propagate through the feed-forward neural network. It means that when we want to write the outputs y1 to ym, when we have inputs x1 to xn, we call this process of calculating the output from the inputs the forward path in neural networks. It means that we are going from left, it means the input layer, to the right, which is the output layer. Yes. Okay, in this process we track the values from the input to the output layer. Okay, to present forward path compactly, we need to define some notations that you will see. Okay, we can get rid of biases by defining a new constant node in each layer. As you can see here, each node has a bias. You can see here, as you saw before, we have W1 neurons, and each of in the first hidden layer, and each of these W1 neurons have a bias, so we have WL bias in total. So instead of doing this, we define a new node here. It is a constant input, and we let these biases being the weights of the link between this constant node and the neurons here. Okay, you can see them here, and we do this for all of the layers, from first hidden layer to the last hidden layer, and also the output layer, which we call L plus 1 layer. Okay, so if we are in input layer, oh, please note that we index the layers from 0 to L plus 1. The input layer is layer 0, the first hidden layer is layer 1, the second hidden layer is layer 2, and the hidden layer is layer L, and the output layer is layer L plus 1. Okay, everything is ready. As you know, in layer L we have WL plus 1 nodes, and we assume that W0 is equal to w0 is equal to n, and you may think, why do we have w0 plus 1 would be n plus 1, and you may think that why do we have n plus 1 nodes in the input layer, but you may note that, remember that we have defined a new constant node for bias. Okay. Okay, we can continue this. And also for the indexes in each node, we have index 0 for the bias neuron. It's better to not call it neuron. For the we have index 0 for bias node, and we have indexes 1 to WL for neurons that we have. Okay, and now we can now we can define the W between each node and the node in the next layer. The node I in layer L minus 1 has an edge to node J in layer L. We denote this weight with WL, which is for the biggest layer. You see we have layer L and we have layer L minus 1, but we replace here with WL, and we first replace the destination node, which is node J. So for memorizing it, you can see that first of all it is for the destination, and the last for the origin. The destination is layer L, and the destination is node J, and the origin is I. Okay, so you can see here, for example, we are in layer 0, we are going to layer 1, node J. So here it is in layer 1, node J, and the origin is from node I. And samely here you can see it is WL, it means the next layer is L, and yes, it's the same as the previous example. So what's next? Okay, one important point is that the weights coming out of I equal to 0 are biases. You note that if you remember, we indexed the nodes from 0 to L, and the zeroth index in nodes is the bias node or the constant node, and we know that the bias here, yes, it is bias. Okay, and we know that there is no link from a node to a constant node, so the J never can be 0, because if J is 0, it means that we have a connection from a previous layer to the bias in that layer, but we know that the bias has no input, it has only output. And please note that we have assumed it exists. Yes, I think you know what I mean. Okay. So the outputs that we have can be of 3 types. Type 1 can be the bias, which has the output 1. The weight of this edge specifies the bias that we have. Type 2 is the input, that's always the output is equal to the input. And type 3 are the neurons that that the output is the output of the activation function, and we don't know pre-assumedly the function, the output, but the type 1 and type 2 we knew the outputs from the beginning. Okay, and we want to know the outputs. If j is equal to 0, it is a constant node, so the yl 0 is equal to 1, and if l equal to 0, it is the input layer, so the y0 of j is equal to xj for j from 1 to n. And for neuron j in layer L, we can write WL of j is equal to f of L of z of L of j. And the z of L j is the output of the affine function in neuron j that is defined here. Okay, by now I hope you have understood the architecture and the definitions that we had until now. Okay, now we can go to the next slide. You can see the forward pass process as we discussed before here. Yes, I'm going to skip this part. Oh, yes. It is the formulation that we had in the previous two slides. Z of L in point J equals to this summation, and we can rewrite this summation as the product of these two vectors. Okay, we can further extend the vectors notation by defining Z of L equals to this matrix. This is Z of L in point 1 to Z of L in point WL, and thus writing Y of L as Y of L equals to F of L in point Z of L, where F of L is applied in 3 Ys. Okay. As you can see, we can write the forward pass in fully connected feed-forward neural network as the following. We have a loop over L which starts from 0 to L, and we have a loop over J which starts from 1 to WL. L is showing the number of the layer number is from 0 to L, and the J shows the width of the layer that we are in. So in line 4 you can see that we add y of L in point 0 equals to 1, and set Z of L plus 1 in point J equals to this term that we had proved it before, and then we compute this line on line 6, compute Y of L plus 1 equals to F of L plus 1 Z of L plus 1. Okay, and as you know, F is the activation function. Okay, and we can define the matrix W as the term that you see here, and WL has WL rows and WL minus 1 plus 1 columns, which is reasonable based on the things that we have talked about before. Okay, and the forward propagation algorithm is as follows: is the is same as the pseudocode that we had before, and the linear layers are the layers that their weights are learnable, and the nonlinear transform that is specified by activation. The output of this layer passes forward to the next layer till we get to the output. Here is the compact diagram, and yes, nothing more. We can go to the next section of this chapter. Okay, we are in the section 2 of chapter 2. When the fnn is fixed and all the weights and varieties are given, forward pass determines the label of a given data point x. We need to train the network, and we have defined the loss and train, and we want to train the loss via a gradient descent algorithm. So we have to determine the gradient, and we have the backpropagation algorithm that we want to discuss in this slide. Okay. We have some true labels which we denote as v of b, and the forward pass outputs are the outputs of passive function. You can see the passive function here, and we have some data points x of b. We forward pass it through the network, and we get y of b, and this outputs we want this output to be equal to v of b, which is the true or actual label. So the optimal ways that we are searching for is as follows: w star equals to argmin of the risk. And what is the risk? As we have seen before, it is the argmin of 1 over b sigma of loss between y of b and v of b. It is the training process. And if we want to, we can replace the y of b with passive x of b with respect to the weights w. So we can write this algorithm as the 6 lines pseudocode here. We initialize the weights and deviation. We set the deviation to the plus infinity, and because we set it to infinity because it's the termination criterion for our loop in line 3. We choose some small epsilon and eta. Eta is the learning rate, and set t to 1. We want to increase t over time. Okay. We want to update the weight in line 4. We update w in time t as wt minus 1 minus eta times gradient of r in point wt minus 1, and we update the deviation to see if we should terminate the loop or not. The loop means the training process. The main challenge is to how to calculate the gradient of r in point w in time t minus 1. Okay, the short answer is using backpropagation, but we have to see how to do this. Okay, the w is always consists of always and biases, and as you can see in the picture, you can see the w. W is all the model. Yes. Okay. And now we want to try to open up the gradient. We need the partial derivatives of r of w with respect to wl of j and I for yes, as you can see, if we want to find the round or gradient of r of w with respect to the wl of I and j, we can rewrite it as follows, and yes, you can see the equation here. and it's enough to develop an algorithm that computes partial derivative for a single data point. Okay. So it would be our algorithm, and we can replace y with passive of x with respect to w, and we know that y is a function of w. It is obvious, I think. And yes, it's enough with this part. And the most important thing to note is the chain rule for derivation. So if we have y equal to f of g of x, if we want to derive it, we'd have d of y equals to f dot of z times g dot of x d of x. It's important to have this point. It is the chain rule and the core part of the backpropagation algorithm. Okay. And we can now understand that d of y is equal to d of f of g of x, d of x over d of x. So yes, and the final thing that we want to conclude is this, that d of y with respect over d of x is d of y over d of z times d of z over d of x, which is chain rule. Okay, and if we want to extend this idea to deeper nested function, something like induction, if we let z1 equals to g1 of x and z of n plus zn plus 1 equal to gn plus 1 of z of n for some n, then we can derive y with respect to x in this general formula that we have here. Yes, and we can also show this chain rule using a computation graph for the deep nested function given above. And yes, you can see this computation graph here. We go from x to z1, blah blah to zn to y, and we go back, which is the backpropagation process, f dot, g dot, and so on. And so we want to derive the output dy over d of x. We can write it in this form, so it would be f dot of zn g dot n of zn minus 1 to the last one, which is g1 dot of x. Yes, it's the chain rule. And here is an example that you can see here. Yes, we can compute the gradients and so on. Let me see if anything remains here. Okay, so the derivatives are easily determined recursively. d of y over d of z3 would be 1 over e, and d of y over d of z2 would be the product of 1 over e and e, which is 1, and d of y over d of z1 would be the product of 1 times 2 and 2 times 2, and 4 would be the derivative of the output with respect to the input. Okay, so as you may understood, the backward pass is only possible if you have already taken the forward pass. So in multivariate form we have the same process. Sorry, and yes, I think this place has nothing more to say, and we can pass over this part. And yes, for example, if we have multiple paths, we may have multiple paths from input to output, so we have a summation. For example, if you want to find the d of y over d of x, you should have a summation over all of the possible paths from the output to the input, I mean in the backward path. Okay, and if we have a single neuron, we can find the derivative of the loss with respect to the W's and biases as follows, as you can see in this picture. Okay, and yes, so I think these parts are not that much of importance here, so I'm going to skip them. You can read them if you want, but I think the most important thing is to be able to compute these things. And you know, the local operations that are computed here, I think they are not important. Why? Because I think the main process is the main part is the chain rule, and nothing is more important than chain rule. So the local operations is nothing more than chain rule. If you know chain rule, you can compute all of these things. Okay, you can see the backpropagation algorithms. We first pass forward pass one time and then backprop one time, and this is the backpropagation. Yes, you can see an example. It is exactly the backpropagation example that we have seen before. Okay. Yes, I think I wanted to show this place. The gradient descent algorithm works in this way that first we initialize values WL and set a learning rate eta. Then we have a while loop. We continue while it's not converged, and we have another while for b from 1 to b. And first we forward and then we backward. Forward propagation and then back propagation. And then updating the rates here. Okay. Yes, that's it. And we go to the next section of this chapter. Okay, we are in section 3 of chapter 2. We want to talk about binary classification V of NN, and for example, you can see, for example, there are some handwritten numbers which we call MNIST. Yes. Okay. For example, we have a hyperparameter. What is a hyperparameter? For example, the number of hidden layers. So we set the number of hidden layers 2, and the depth is hence 3 because the depth is equal to number of hidden layers plus 1. We specify the width of each hidden layer, and then we specify the activation and output layer as a single perceptron. We have defined our model here, and yes. Okay. We have defined the loss, but are you sure that it is a good or bad choice for the perceptrons activation? It's not good because it only counts the number of misclassified samples. It's not good because we have only 3 linear operation here. we have our forward pass in a very straightforward, and we compute our output and the middle outputs. Okay, and it is our graph that we have, and then we want to compute the backward pass. You can see that when we want to find the derivatives here, if we find derivative with respect to output, and we set it like this that you can see here, and then we compute the gradients, and we repeat it for every image in the batch, and then average gradients. Finally, we move one step in gradient descent and find the weights of the next iteration. And in fact, the empirical risk is not a smooth function of the weights and biases. Therefore, using gradient descent, we do not end up with a well-trained network. Okay, and we have understood lots of things to this point, and we know what is you have understood that this first round with the neuron whose activation is not good. You saw that it's not good, so we have to have a good approximation of set of step function and differentiable. We have seen the sigmoid function, which is as follows: sigmoid of x equals to 1 over 1 plus e to power minus x, and it's very close to the step function with this difference that it is differentiable. So it is instead of step function, it's better because it resolves the differentiability issue. So now we have sigmoid function, but the problem is that the output of the networks is now not binary. We now interpret the output as a probability, so we should rethink about the loss function now. Okay, so the indicator error is not good anymore, and we should think of other losses. We would discuss two methods: MSE, mean squared error, and cross entropy. These are two popular losses. Mean squared error is the error of the actual is the difference of actual and the predicted output to power 2. It is differentiable. It's good but not best. Another one is cross entropy. It is minus v log of y minus 1 minus v log of 1 minus y, and you can see yes, it's proportional to Kyle divergence, but it is not called divergence. It's similar to that, and the differentiation is as follows that you can see in the picture. Yes. Okay. And if you want to talk about classification, it's not necessarily binary, so we find something better. And we also should note that sigmoid gives us something between 0 and 1 if y3 is equal to or is bigger or equal to 0.5 or something like that. It's a parameter, we can set it. We label the new image as handwritten 2, and if it is else otherwise, it means if y3 is less than 0.5, we label the new image as not being handwritten 2. Okay, but we should have multi-class classifications because the binary classification is not answering our needs anymore. Okay, so we should have a vector activated neuron that gives us a vector instead of only one number. Yes, as you can see, it's out with y1 to yc, and yc is computed using the softmax function, which is as follows: e to power z of c over sigma of e to power z of j, and we iterate over j in summation. Okay, and softmax always represents the probability distribution of the set of classes because its summation is equal to 1, and we can use it to extend our feed-forward neural network to multi-class classifier, and we replace layer 3 over the output layer with a softmax activated multivariate neuron and treat its outcome as the chance of input belonging to each class. And yes, you can see how our new algorithm works in this way. It's softmax activation, and we had 1, and yes, it's, you know, it does not anything more to talk about. I think we can go faster in the way. Okay, as you can see, MSE or mean squared error is good, but not the best. The best is cross entropy, and we can just extend them to multi-dimensional vectors, as you can see here. Yes. Okay. Okay. Oh, here we have Jacobian matrix that maps C-dimensional to C-dimensional, where 1 to yc is equal to f of z1 to zc. When we use this function, we can say any integer y of j is function of alt of 1 to alt of c. So we have gradient of y of j with respect to z is equal to this point. Okay, it's somehow hard. I'm trying to understand it. Yes, okay. So we can collect all these gradients into a matrix, which we call it Jacobian matrix. Okay. I hope you all saw this. Okay, we have seen the Jacobian matrix here, and yes, we are end with our gradient descent. I hope you understood everything well, and we go with the last section of this chapter now. Okay, we are in the last section of chapter 2. We want to talk about what is full batch, what is mini batch, what is one batch training. Batch is the data set reserved for training, and in full batch training we calculate the gradient for all data points in the batch, so we needed to wait for to forward and backward pass all data over the network. And yes, yes, we can go over this parts. Okay. You can see it takes time long for our full batch training. For example, if we need 100 iterations of gradient descent, we need to pass back and forth for 6 times 10 to power 6 times. Yes, it's very huge because we have 60,000 numbers in this dataset. It's impossible in large neural networks and for large datasets, so we really don't need. We can do training much faster because the full batch training is really not practical. In practice, we use the stochastic gradients or mini batch gradient descent to train our neural network with feasible complexity. You can see the algorithm here. You can read it in the future if you want, and then we mean over the values that we have calculated, and the full batch training is equal to sample level training. Yes, and it's very important point from my point of view. Okay, so At each data point, we calculate a noisy region of a ground truth gradient, and yes, the sample level reverse propagation is equal to full batch, and we say that G is an estimator of the ground truth estimator. And we have some cyclic behaviors. We can end up with our initial point at the end of the batch, and for instance, consider this scenario. We start with some WL of 0 and get into the batch for the first time, and we update W's. And we assume that the last W is equal to first W for all layers again. If we further loop over the batch, it is useless, and we always get to the initial point, and we now have the repetitive cycle issue. Okay, and how can we avoid this? We can use a stochastic gradient descent each time we are to loop over all our training batch. We shuffle the data points randomly. This way we avoid next loop behavior. We avoid next loop behavior like the previous. So the stochastic word comes from this part that we shuffle the data points. And it is the most common algorithm for training of neural networks, and random shuffling is that we randomly permuting the data points, and yes, and please note that the sample level training does not lead to problems like the cyclic issue that we said, but we have to accept that it's drawback as a cost we pay for less complexity. It is a trade-off always, And for random variable x with mean mu, where variance is defined as this thing that you can see, and when x is 0 mean, we can say variance of x is equal to expected of x to power 2. Yes, so if we have n independent random variables, then we have variance of the summation equal to the summation of the variances. It's very important. So if they are 0 mean, we can say that the variance when we sum some variables, the variance of an average drops by 1 over the number of samples. It's very important note. And so yes, here we're doing the same thing, and so the variance here drops. Always we have complexity accuracy trade-off, and okay, you can see mini batch stochastic gradient descent here. Okay, it is a complexity accuracy trade-off. If we have if the complexity is very high, you have full batch, we have mini batch, we have stochastic gradient descent. All of these things are different from each other. The variances differ. If we have only one sample, if you find only one batch, sorry, if we have one batch, it is full batch gradient descent. It takes lots of time for us, the variance decrease. If we have if base size is equal to 1, it is a stochastic gradient descent, the variance is very high, but the time is very low. Yes. Okay, batch size is the size of batch, the iteration, and it is how many times you iterate over a batch, and the epoch is the number of the number of times you iterate over whole training dataset. Yes. Test risk is the test loss. Test accuracy is the portion of accurate predicted samples. Okay, and you should note that we split the data into two parts: the training part and test part. For example, for MNIST it is 60,000 for training and 10,000 for testing, and the number of classes it's 10, so it is a non-binary. This is multi-class classification task. We use cross entropy as loss function, and for example we use 100 epochs. We use mini batch stochastic gradient descent, and the base is 100. We perform 600 iteration of gradient descent because we have 60,000 samples, and we have base size of 100, so we have 600 base. So in each epoch we iterate 600 times, and yes, as you can see, it is the test loss, it decreases over time. It is the test accuracy, it increases over time. And yes, I think we are finished with this chapter. We have talked about the fundamentals of deep learning, and some parts we talked about the fundamentals of machine learning, and in future we also talked about some initial points in machine learning and deep learning. I hope you enjoy it and learn from it. Thank you and goodbye.